Okay, so welcome to Complex Analysis, Math383. This is lecture 15. And what I want to do is I want to talk a little bit about some of the stuff from the video last time, which was the Roche's theorem, the OpenMapping theorem, and the maximum modulus, which I believe we did not prove in the video last time. So I want to talk about the proofs. I want to use a lot of the time today to go over some of the key concepts from real analysis that we need. It seems like not every fact that I would like to have at ready disposal in real analysis seems to be there. And so I want to spend a little bit more time on that. So going forward, I'm probably going to adjust a little bit how class time is used and have you do some more reading and whatnot or watching videos at home, and then free up class time to have more discussions about some of the topics and some of the prerequisite materials. Okay, so again, I'm going to start off by reviewing the argument principle and Roche's theorem, and then talk about some of the big consequences, which are the OpenMapping theorem and the maximum modulus principle. Related to this is not only the real analysis review, but to just sound like a broken record. Real and complex are completely different subjects. The intuition for real does not extend to complex. And the reason is it is a tremendous condition to be complex differentiable. You should think of this, if you remember your Green-Gauss-Stokes theorems, if you've seen those, you are essentially in a situation where you have a conservative force, so all line integrals are zero. That is not a generic case. And it's not surprising that if you are in a highly specialized situation, that you get a lot of different results. And that's why the flavor is so different. So as a rule of thumb, you should always try to build intuition whenever you see something new. You should say, well, what have I seen that's similar to this that I can use to try to get a sense of what the answer might be? The problem is every time you do that with real analysis, you will be almost surely misled. Oh, thank you. Someone is trying to come in now. Excellent. So somebody was trying to come in earlier, then they left, now they're back again. Excellent. Okay. So we had the argument principle, which was if we integrate f prime over f, and of course we multiply by 1 over 2 pi I, then this counts the number of zeros inside C minus the number of poles. So basically every zero is counted positively, every pole is counted negatively. What kind of number must this be? Integer, right? It is amazing the consequences we have from the fact that this must be an integer. If I give you a continuous integer valued function, what can you tell me about it? It's constant. So that is not something that might be immediately apparent as to how powerful that's going to be. There are lots of ways to prove this. I think the way we proved this in the video last time was, we wrote our function as f of z was an z minus z naught to the n times b of z, and then we showed that f prime of z over f of z was equal to n z minus z naught plus b prime of z over b of z. And then we just went through and did the analysis like that. Another way you could actually do this if you want is you could write f of z. Now, does the an really matter? What are we integrating? We're integrating f prime over f. So if I rescale my function by 15, it affects the numerator and the denominator the same way. So really, the an is not going to come into play at all. So I'm not surprised that the formula is independent of an. So if I considered a function of the form z times z times z, say n times, and then times b of z, we would get f prime of z over f of z is 1 over z plus ... plus 1 over z plus b prime of z over b of z. So this is extremely similar to what we did before. I just collected all the z's together and said, z minus z naught to the n. Really, I could keep them all separate. And what I'm saying is, if I take the derivative and then divide by the function, it's the same as looking at each piece, take the derivative, divide by the function, add the next piece. This is often called the logarithmic derivative. And it comes to the log of a product is the sum of the logs. So if I could just take logarithms, if I take the log of f, I would get the log of this, which would then be the sum of the logs. And then when you take the derivative, well, it's now a sum, so you would take the derivative term by term by term. And then when you divide by the function, it would come out beautifully like this. So as a nice exercise, show that if you take the logarithmic derivative, you get the following. The problem is we haven't defined the complex logarithm yet. So we can't just take the logarithmic derivative because we don't know the logarithm yet. This reminds us of the earlier part in the semester when we had to be so careful we could only integrate over triangles and then squares and rectangles. We have to be a little bit careful at this point because we don't know the complex logarithm. But we can approximate a lot of its properties like this. And so it's a good exercise, show that if you do the logarithmic derivative, and just assume everything works, you would get this beautiful formula. And now because b prime of z over b of z is holomorphic, when we integrate that, it contributes nothing. Each one of these is going to contribute 1. Okay. So in the last lecture, we talked about Rouché's theorem. Depending on which book you look at, they can define Rouché's theorem slightly differently, so you've got to be careful. This is similar to physicists and mathematicians have slightly different conventions for, for instance, spherical coordinates and whatnot. You just have to be careful whenever you're quoting from a book. So here we're looking at the functions f and f plus g. Sometimes people look at the functions f and g. Okay, really not a big deal. G is just f plus g. Just be careful which book you're using. And it says if f of z is strictly greater than g of z on the boundary, then the functions f and f plus g have the same number of zeros inside the circle. And this came from looking at this beautiful function, 1 over 2 pi I integral of ft prime over ft, where ft is f of z plus t g of z. And when t equals 0, we just get f of z. When t equals 1, we get f of z plus g of z. So we're slowly interpolating up from f of z to f of z plus g of z. And the key idea was for every choice of t, this is an integer. And then if the function is continuous, it has to be constant. So in particular, its value at t equals 0 and its value at t equals 1 has to be the same. Therefore, these functions have the same number of zeros inside. So this all came down to the fact that this is a continuous function. And we often just gloss over this. Well, clearly this is a continuous. Well, how would you prove that this is a continuous function? Well, some things that are helping us is we're integrating over the boundary of C. We know that our function has no zeros on the boundary, right? So we know the function ft prime over ft is at least well behaved. And what we want to do is we want to show that this is continuous. So we could look at, for example, n, let's say t1 minus n of t2 would be 1 over 2 pi I, the integral over c of ft1 prime of z over ft1 of z minus ft2 prime of z over ft2 of z dz. And we want to show that this is a continuous function in T. Now, our function is really nice as a function of T, right? We could roll up our sleeves and just try to do the analysis directly because we happen to know what function we have. It's just f of z plus t g of z. Okay, well, if I have t1, if I have t2, I can put everything together, I can go through, and I can just do some algebra. So substitute, show continuous, and then we have a continuous function. We're integrating it over a curve of finite length. And if t1 is close to t2, what should be true? Well, right, but what should be true about the integrand if t1 is close to t2? It should be very small. And that should be coming from continuity. So now this is where we get to play Who Remembers Real Analysis. I'll be your host today. All right. Who remembers uniform continuity? So you could appeal to uniform continuity here. So continuity is, I give you an x and an epsilon, you find a delta, such that if I'm within delta of x, then the value of the function is within epsilon of f of x. What is your delta allowed to depend on? Epsilon and x, right? I give you an x, I give you an epsilon. Well, you get to use both pieces of information. If I give you a parabola, and you want to be with an epsilon, if you take x down here, then to be with an epsilon, you could have a somewhat wide window. But if I take x further down, and I want to be within that same window, my function is growing much faster. So if I choose the same epsilon, I'm going to have a much tighter restriction. So in general, delta depends on both x and epsilon. A function is uniformly continuous if, given an epsilon, you can find a delta that works simultaneously for all x's. And so if there's time at the end of today, we'll talk a little bit about how would you do something like that. But this is a great place to use uniform continuity. More, what we might have is maybe we have the integral over, let's say, some finite curve of a t1 x minus a t2x dx. That's really what we have. It's something of this form. And here the function a is just going to be ft prime over ft. And instead of x, I guess I should be using z, but I'm using x. Okay. When you look at this, what do you think of if t1 is close to t2? What does this look like? So I'm evaluating a at t1 x, and then I'm subtracting it at t2 of x.
Almost like if that's less than delta, then you have the other part of the flexibility.
Yeah. But does this look like anything you've seen before? It's looking a lot like zero. What if I divide by t1 minus t2 and multiply by t1 minus t2 dx? Now this piece is looking like a derivative. It's actually looking like a partial derivative. And so if I know that the partial derivative exists and is uniformly bounded, then I could replace this part over here with a bound. t1 minus t2 is going to be small. The curve has finite length. And then this should give you another proof. So if dA dt exists and is bounded, then we're done. Okay. And it's a good exercise to try to put in all the details of this. And so again, if my function is differentiable, then in the limit as t1 goes to t2, it's going to just be the partial derivative at that point. So if I'm close to it, I should be very close to that as well. We should be able to quantify things. So these are two different ways of trying to make the following statement rigorous, that we really do have a continuous function. Just because I say the function is continuous doesn't mean it's continuous. But using standard techniques of real analysis, and we're not really using things that are true about real valued functions, we're just using some of the proof arguments from real analysis, they just apply. Okay, so now Rouché's theorem has two wonderful applications. The first is the OpenMapping theorem, that if f is holomorphic and non-constant, then f is open. So that means the image of an open set is open. And then that has as a consequence the maximum modulus principle. If f is a non-constant function that's holomorphic, then it cannot attain its maximum in the interior. Okay. And by maximum, I mean, the absolute value. Okay. So whenever possible, you always want to consider real cases. So can somebody give me, a function f that takes an open set to not open? So you need to give me a function and you need to give me an open.
Well, that's boring.
Yeah. And we're assuming f is not constant. This is why we always have to say, we exclude the constant function, because if I take the constant function, then an open set is not mapped to an open set.
Like create a function like sine on an open interval that's larger than.
Good. So if we do, sine from, let's say, minus 2 pi to 2 pi, that goes to minus 1, 1, which is a closed interval. The example I like to use is x squared takes the interval minus 1, 1 to the interval 0, 1. We have 0, but we don't have 1. So somehow things have to be very different in the complex world. And so if I do, f of z is z squared, well, now rather than looking at an interval, I'm looking at, say, a disk centered at the origin. And what it will do is the upper half of the disk actually expands and fills the whole thing. So if I look at the function, because what's going on is if I write z as r e to the I theta, then z squared is r squared e to the 2 I theta. So the upper half disk, when I square things, I'm doubling the angle, goes all the way and covers everything. So really, when I look at the function f of z is z squared, I'm going to cover the disk twice. The upper half covers the whole thing, and then the bottom half covers the whole thing. So the thing to remember is real and complex, very different behavior. So when you try to build your intuition, looking at generic real-valued functions is not a good idea, because generic real-valued functions have just a lot more flexibility. They don't have the same restrictions. All right, so let's look at the proof that the book gives of the open mapping theorem. Is this large enough that people can read it? Okay, because I want to mock up the proof. And I feel I am allowed to do this because I was the grader for one of the authors of the book when he was a freshman. So, all right. So if f is holomorphic and non-constant in a region, then f is open. So what we want to do is we want to show that if I give you some omega, and so let's say we start off with, here is my point z sub naught, and it's going to be mapped to some point omega naught. Then I want to be able to show that if I take a sufficiently small neighborhood about omega naught, you give me anything in here, let's call that w, I can find some point over here, z, that gets sent to it. Do you want to call that point z that gets sent to w? Or do you want to give it a better name? What might be a better name than calling it z? ZW. If I look at it ZW, oh, okay, yeah, ZW is the point that's sent to W. That just makes it a little bit easier for me to keep track of what's going on. It's not a generic point Z, it's a very special point, and that point depends on the W. You vary the W, I vary the Z. Okay. So we have to show that no matter what point I choose near W naught, as long as my disk about W naught is sufficiently small, there's always going to be something that's mapped to it. Maybe if I choose a very large disk, I'm going to have trouble and not everything is going to be hit. But if I make the disk sufficiently small, and that's all I need for an open set. A set is open if about any point you can draw a little disk and everything in that disk is in your set. Depending on where you are, the size of the disk is varying. Does everybody see this beautiful black boundary around the white slide? So if I choose a point, over here in the middle, like over here, I can draw a very large ball and stay away from the boundary. But if I choose a point down here, I clearly can't draw a ball as big and still stay away from the boundary. Okay, so we want to choose z appropriately. So we say, let's look at the function g of z is f of z minus w. And we can write that as f of z minus w plus, I'm sorry, f of z minus w naught plus w naught minus w. So we've done the classic trick of doing nothing, right? We've done nothing by adding 0 in a clever way. Why is this a good way to do? Well, we're going to call the first part f of z and the second part g of z. Can you find a z such that f of z equals w naught? Yeah, z naught. In fact, that's what started the whole shebang. So then the question is, can we find a z such that f of z will equal w? Well, if f of z equals w, that's the same as just saying g of w is w. I mean, what is f of z? F of z just simplifies to, I'm sorry, f of z minus w naught plus w naught minus w. This just simplifies to f of z minus w. So we're trying to find where is this function 0. If we find a place where this function is 0, then we found a z such that f of z equals w. So finding a z such that f of z equals w is the same as finding a z such that g of z is 0. Why do you think I might want to try to find a z such that g of z is 0? Why might I want to rephrase the problem to trying to find a z such that g of z is 0, or prove that there exists a z such that g of z is 0? Why might I want to do that? Yeah, to apply Roche's theorem, right? Foreshadowing the art of a great lecture, right? There's probably a reason why we did Roche's theorem. I said, today we're going to look at consequences. We want to be able to use Roche's theorem. Roche's theorem counts zeros. It counts how many zeros do we have of certain functions. We're writing our function little g as the sum of two functions. For the first function, f of z, do we know if f of z has a 0? Yes, by construction. So we know f of z has a 0. So if we can just show that f of z plus g of z has the same number of zeros as big F, then we know that little g has to have a 0. So the whole point is we know that big F has at least one 0. If we can show that big F plus big G also has at least one 0, then little g has a 0. I don't like writing this as g of z. And since I'm lecturing, I get to change notation if I want. How would you want to write that? No, I do like the G, and I like the Z in here, but I would put in one other thing. W naught. I might just put that in there just because that would remind me that this is coming from the point W naught that I've chosen. You don't have to do that. They just wrote it as G of Z. I like to have notation that is highly suggestive. The more years you spend on a subject, the less important it is to have that notation. But when you're just starting out, it's nice to have very explicit notation so you can glance down and see what's going on. All right, so our thought is that we're going to use Roche's theorem. We know big F has at least one 0. So if we can show that big F, now let's see, we've got to look and see how is Roche's theorem phrased. We want big F, we want our function to have absolute value greater than G, then F and F plus G have the same number of zeros. Okay. So what we're doing here, we want to show F and G have the same number of zeros. Okay. And so again, what we had before was if the absolute value of F is greater than the absolute value of G, then F and F plus G have the same number of zeros. Okay, so now choose some delta such that the disk z minus z naught less than or equal to delta is contained in omega. Well, this is like an ante to stop the conversation. My function is defined in omega. If I'm going to localize to be around z naught, I better stay inside the omega. So at the very least, I need delta to be sufficiently small so that I'm contained in omega. And now I want to choose delta also such that f of z does not equal w naught on the circle. Is that possible? But maybe it equals w naught at one point on the circle. It doesn't have to equal w naught everywhere on the circle, but maybe there's one point on the circle. Why? Otherwise, it accumulates. So if this was false, if I have z naught over here, then imagine on every circle, there would have to be at least one point where the value is equal to omega naught. And then those would have to accumulate somewhere. Where would they accumulate? Z naught, which makes sense because Z naught is W naught. But we would have to have a sequence that accumulates. And if it accumulates, if always can find a point on a circle with f of z equals W naught, it accumulates. And thus, f is what? Constant. So this shows you how careful you have to be when you're reading math. The accumulation theorem was implicitly used here, but it was not stated, it was not extracted, to say that this is what we're doing. Why are we able to do something? You always want to be quite clear what gives us the power to assume that we can find a circle where f of z is not equal to W naught on that circle. And the answer is the accumulation theorem. So we now know that we can find a delta such that f is not equal to W naught on that circle. Okay, now what we're going to do is we're going to say, let's look at W minus W naught. We're going to make this small. And again, we can do that because we can choose the size of the circle we want to look around W naught. We're not trying to show every point is in the image of f. We're just trying to show all points sufficiently close to W naught are in the image of f. Well, if we just have to show sufficiently close, I can take sufficiently close to be however small I want. And if I have trouble, I'll just zoom in even more. And so let's choose an epsilon so that we're going to look at all the points W minus W naught less than epsilon. We want f of z to be strictly greater than g of z on the circle. Okay, is that always going to be possible? Why?
We assume that's not possible with the argument theorem. If we have a zero at the boundary, it will blow up. The argument theorem will blow up.
But we're saying now we want f of z to be greater than g of z.
Yes.
So why is f of z greater than g of z on boundary?
Choose explicitly, if we take the moduluses around on the circle,
Yes.
basically that's it maps to the rules, and we must have a minimum number. Otherwise,
Good.
we'll accept
So now we have a theorem from real analysis that we're using, right? A continuous function on a compact set attains its maximum and minimum value, right? So we might prove that at the end of class today, depending on how much time there is. How many people remember a continuous function on a compact set attains its maximum and minimum? Okay. Good number of people do not remember that result. Do not raise your hand, but just think mentally, how happy would you be if I said, close your books, we're having a pop quiz right now, prove that any continuous function on a compact set. This is why I want to re-image how I'm doing the class. I want to spend a little bit more time reviewing some of the real analysis material and move some of the more standard complex analysis material to having you do that at home. And if you have questions on that, we'll talk about it in class. But I think we need to spend a little bit more time reviewing real analysis. There's a lot of stuff that's being done implicitly here. And after a while, you know the subject so well that you just read it and you read the words and you read the proof there without it being written. Okay, so here, why is this true? Continuous function on compact set attains max and min. Min of f, of absolute value of f, is greater than 0 as not 0 on boundary. Then just choose epsilon less than 1/2 of the minimum of f. I like to put the extra 1/2 to just cover myself, just in case I make any mistake later on. I've got a little bit of a fudge factor. But you're seeing that there's a lot of things in this paragraph that were not written down. As you go further and further in mathematics, there's less and less that's actually written down. And this is one of the dangers as you read the books, is a lot of these statements are not done clearly. All right, so now we can show that f of the big F is greater than big G in absolute value on the circle if epsilon is sufficiently small. So now that that's the case, now we can use Rouché's theorem, and f plus g will have the same number of zeros as f. And since big F has a 0, big F plus g has a 0. And that's the proof of the open mapping theorem. But again, there was an accumulation point argument that was hidden. There was a continuous function on a compact set attains its maximum and minimum that was hidden. Okay. The last thing that's worth mentioning is that it's not surprising to use Rouché's theorem here because this is in the chapter and the part of the chapter that immediately follows Rouché's theorem. The hard part as you go further and further in life is to figure out what do you use and when. So I think some of you have heard my baby crying view of mathematics. When a baby is crying, what do you do? And this is really dangerous asking a question like this, but what should you do if the baby is crying? And instead of doing that, let's modify that to hold the baby. So we'll do hold the baby. What else can you do?
Flip it upside down.
Flip it upside down. What else can you do?
Let it dry.
Let it cry. Toughen up. Good. What else? Eat it.
No, not eat it. Eat it.
Oh, what was it? Oh, feed it. I thought it was the microtraction. Much. I mean, you eat it would definitely solve the problem. Okay, feed it. Good. What else? Missing some obvious things for babies crying.
Put a pacifier.
Put a pacifier in it. You, even if the baby still cries, you might at least not hear it. What else? You are the change the diaper. There's lots of different things you can do. And initially when the baby is crying, you don't know why the baby is crying. You can ask the baby, but the baby's not going to give you any useful information. After a while, you start to notice, that's the I want to be fed cry. That's the I want to be held cry. That's the I want a new diaper cry. I want my pacifier. I want to be eaten. Usually, you don't get the I want to be eaten cry too often. But the more times you experience it, the faster you can identify what the cry is. When you are young and just learning a subject, it's very hard to look at something and know what to use. When you have homework problems from section 3.2, and section 3.2 is on Rouché's theorem, probably going to want to use Rouché's theorem. This is not rocket science. The difficulty is when you have an exam, what do I want to use? So you ask, what does this look like? Can I reduce this? Can I convert this to something I have seen? Okay, so the next one is the maximum modulus principle. If f is non-constant, holomorphic in a region omega, then f cannot attain a maximum in omega. Do you think it could obtain its minimum in absolute value? Yeah, can you give me an example?
squared, f of z equals z squared.
Give me something even easier than z squared. Z, right? But look at f of z equals z on a disk centered at the origin. It's minimum in absolute value. So the question is here, are we talking, when we say maximum, are we talking about the maximum in terms of the absolute value or just the maximum number? Which doesn't really make sense. And that's the reason why there was an extra credit problem early in the semester. You can't order the complex numbers. You can't come up with an ordering that has all the properties you want. So we're going to talk about just the absolute value of the function. It is possible that the minimum value of the function is attained in the interior. Okay. So here's the proof. Suppose f did attain a maximum at z naught. All right. So we're going to assume, for the sake of contradiction, that there is some point z naught where it's maximum. So here is z naught, and I apply my function f, and I get now this point here, f of z naught. Now, we know we have an open mapping. So what that means is if I draw a small disk about f of z naught, there's got to be something around z naught that maps to f of z naught. And so if you think about what's going on, if this is the origin of the complex plane, if this is 0 plus 0i, then if I just connect this and go a little bit further, I have to be a little bit larger in absolute value. That's essentially all it's saying. If f of z naught happens to be 0, then the proof is even easier. Go in any direction. But because it's an open map, I can go a little bit further, and I'll be a little bit further from the origin. Okay? Do you think this holds for real valued functions? If I give you a continuous differentiable real valued function, does it have to attain its maximum on the boundary? So give me an example. Okay, well, this is saying f cannot attain its maximum in the interior. So can you give me an example of a real valued function which attains its maximum in the interior? Yes. All right, so what would be your function? Okay, so f of x equals sine of x, and then I would be, say, minus 2 pi to pi. Another fun one would be 1 over 1 plus x squared. Or another one would be, e to the minus x squared. All of these are very different. And it's nice to then look at these and ask, what would go wrong if I complexify these? One of them, clearly something is going to go wrong if I complexify. Which one is clearly going to have an issue? Yeah, 1 plus x squared actually has 2 poles. And so there's going to be clearly some issue with that. I'm not going to stay holomorphic. But again, you always try to build up some intuition from real analysis, but be very skeptical about whether or not it's going to propagate forward. And then try to figure out what's changing things. Okay, so rather than going through some of the homotopy and deforming curves, I want to just spend the last couple of minutes talking a little bit about real analysis. Okay, so there's a lot of results we need and use from real analysis. And so let's start off with the following theorem. If f is continuous on a compact set, f is bounded. Does that look familiar? So it's not as good as showing that f attains its maximum and minimum, but it's at least a start. Okay, so the proof is by contradiction. Assume not. So for all n, there exists a x sub n such that f of xn is greater than n. Because if it's not bounded, is that right? Yes. So if it's not bounded, then doesn't it have to be greater than n at some point? There's a small mistake here. Yes,
Didn't have the value.
it's an absolute value. I could give you the function negative x squared. Negative x squared is not bounded, but it's not going to necessarily be greater than n. But the absolute value will clearly be greater. Okay, so I can just look at the absolute value of my function. Okay, so if I look at the absolute value of the function, so I get a sequence of points. So I get x1, x2, x3, dot, dot, dot. And what must be true about any sequence of points in a compact set?
They converge to, right, they have a convergent set.
They have a convergent subsequence. So has a convergent subsequence xn1, xn2, xn3, dot, 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 dot. So converges to, let's say, x star. Okay. So if you think about what's going on, I've got my points. Here's x1, x2, x3, x4, x5, dot, 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 dot. And maybe here is x star. Eventually, everything has to be very close to x star. But what do we know about our function? It's continuous. So since f is continuous, for all epsilon greater than 0, there exists a delta such that if x minus x star is less than delta, then f of x minus f of x star is less than epsilon. Contradiction, as the absolute value of f, x, and k goes to infinity. And then, but has to be within epsilon of f of x star. Yes.
Some x sub n and then make epsilon like a half and then x sub n plus 1 escapes. Well,
Not necessarily, because we're just saying f of xn is greater than n in absolute value. Maybe it's also greater than n plus 1.
well then pick it and for which.
So what you could do is you could modify things, and you could say, I want x2 to be at least not only greater than 2, but at least 1 more than f of x1.
Yeah, well, you don't have to do that.
I think it's simple to just do it like this. We have a convergent subsequence. And now that we have a convergent subsequence, eventually it's going to be very close to x star. And so it's going to be within epsilon of f of x star. And now all of a sudden we have our function is bounded. Okay. Any questions about this? Yes.
Is that f of x sub n k? I can't really.
Okay. Which tell me which over here?
That one, yeah.
Yes. That's f of x and k goes to 0, goes to infinity in absolute value. Yes.
Do we actually need to prove like just use direct proof?
Okay.
By like f x star plus some.
Well, how are you, so we want to show that a continuous function is bounded. So how would you do it directly?
So basically, we have everything except the first line. And
Okay,
eventually, all those fxn are bounded by fx star. Like the
but maybe you have to do a different sequence. You just showed that along this sequence, the function is bounded. You have to show for every sequence.
Can we just pick any sequence and just
But different sequences will have different x stars. So you could have uncountably many x stars to look at.
Because like the sequence is countable number of points, but the region is uncountable.
What you could probably try to do is say, what's another characterization of a compact set? Closed and bounded.
And also finite covering.
Finite covering. So any compact set can be covered by a finite union of open sets. So what kind of open sets could we look at here? Can we cover our space with a finite number of disks? And so what we could do is the following. And this would be using uniform continuity. So proof 2, use uniform continuity. Given epsilon, there exists a delta such that if x1 minus x2 is less than delta, then f of x1 minus f of x2 is less than epsilon. And note, delta is independent of x1, x2. Only depends on epsilon. Only depends on epsilon. So now what we can do is, let epsilon equal 1 for, so there exists a delta such that x1 minus x2 less than delta implies f of x1 minus f of x2 is less than 1. Consider our set omega, which is going to be contained in the union of the balls about x of radius 1. So this is ball of radius 1, center x, x and omega. Do we agree that omega is clearly contained in this set, in this union? Yeah, because each ball contains x, right? Now, as compact, as omega compact, we have a finite subcover. So omega is contained in, say, a union, k goes from 1 to n, of the ball about x and k of radius 1. And now for each of those balls, we know everything is within 1 of the center, right? Yep, everything within 1 of f of the center. Take max of f of center plus 1. And so that would be a direct proof that you are bounded. However, what do we need to do for this? Yeah, this is a direct proof, but it's a direct proof using what? Yes? Uniform continuity is one of the things we needed to use. And what else do we need to use? If it's compact, it has a finite subcover. Right? You should check and see, are you comfortable with uniform continuity? Are you comfortable with a compact set has a finite subcover? If not, let me know. And again, I really want to figure out how to balance the complex material with the analysis concepts that we need. It's not bad to see some math multiple times. And one of the things that's nice is we can move some of the material online without any trouble and just readjust a little bit what we're doing in class and just really go through a lot of the stuff that's glossed over in the books. And when you get old, you don't see this anymore. You just wave your hand and just you've seen the argument so many times. When you're seeing it for the first time, that's very different. And so a lot of the stuff is hiding. I would be absolutely fine doing some more stuff and reviewing some real analysis and then just moving some complex around. All right, so this is a good place to stop for today.